Alright, so here are my Chapter 12 homework problems. For the first one, we have a tugboat whose force can be modeled as F equals 81,000 minus 21,000 V with a weight of 3,600 kilonewtons. We know since F equals ma, we can just replace the force with ma. And we know A equals dv dt, so we can put dv dt for A. Then we can split the equation, put like terms, integrate both sides, and come up with this equation here. And since we know that m is equal to weight divided by gravity, we can plug in the weight and gravity and find that the time from V1 to V2 is 18.84 seconds. And similarly, we can plug in, instead of using A equals dv dt, we can do A equals V dv dx. I said dt here, but it's actually dx. So it's m v dv dx is equal to 81,000 minus 27,000 v. Then we can split the equation into like terms, integrate both sides, and then get the difference in position this time after plugging in all the known values, and get 36.14 meters. Number 2, we have a truck moving, pulling a load, a 5,000 pound truck pulling a 1,200 pound load, and the truck is accelerating at 1 foot per second. We know the pulley system equation is just x minus 2y, so we can find the velocity and the acceleration equations that go along with it. In doing that, and knowing that the acceleration of the truck is 1 foot per second, we can solve the deceleration of the boulder should be about half a foot per second. And then we need to do a free body diagram of the boulder, and here it is. So from that free body diagram, we get the equation 2t minus mb plus ma times g is equal to mab, and we can plug in our knowns into that equation, solve for the tension. So the tension in the rope should be about 609 pounds. Knowing that, we can go to the free body diagram of the truck, which gives us F minus t is equal to ma, and then we can again plug in our known values, and we'll find that the horizontal force on the truck is about 764 pounds. And then the force of the boulder on the pallet can be modeled as FAB minus MBG is equal to MBAB. And then just plugging in our knowns again, we have that the force is 1,015.5 pounds. All right. Number 3, we have a tetherball going around a pole. We're supposed to find the angle that it's going, knowing that the tetherball weighs 0.45 kilograms and its velocity is 4 meters per second. So here I drew a free body diagram, and then from the free body diagram, we are able to get these equations, the sum of the forces in the x and the sum of the force in the y. And then we can solve for x on this triangle using trigonometry. And then we just combine those two equations, and it'll simplify down to 17.658 sine squared theta minus 16 cosine theta is equal to 0. And since we know that sine squared theta is equal to 1 minus cosine squared theta, we can simplify it even further. And then from here, we just, through trial and error, I wasn't sure exactly a better way to do it, but through trial and error, I was able to get about 50 degrees. And then since we know it's 50 degrees there, we can just plug in for that original equation, and we get that it's about 6.85 newtons of force, of tension. Number 12, there's a wrecking ball swinging on a crane, and we're supposed to find the tension when it's at rest at the top and the tension when it's at the farthest, the lowest point that it reaches. And then up here on the right, we just have the acceleration at the top is equal to 0 because the velocity is 0, and what the mass of the ball is. From this free body diagram, we can sum the forces in the n direction and come up with this equation. And then since we know that the acceleration at the top is 0, we can plug that in and come up and put the other unknowns in and come up with 122.2 pounds at the top. And we'll do another free body diagram for when it's at the bottom, and we'll come up with this equation. We'll plug in the knowns, and we'll come up with 145.6 pounds at the bottom. Number 5, we have a turntable with a block on it, and the block begins to move, and we're supposed to find the coefficient of static friction between the trunk and the turntable, knowing that it's accelerating 0.24 meters per second squared, and it takes 10 seconds to do so, and the radius it's moved is 2.5 meters. So we know, using the kinematic equation, V1 is equal to V0 plus AT. We can plug in the knowns and come up with 2.4 meters per second. So then we want to model what it looks like from the top. We'll do a free body diagram from the top. We can sum the forces, and we'll come up with this equation here from the top. And then we'll want to model it from the side, do a free body diagram from the side. And we'll come up with this force equation. Combining the two, and knowing that F is equal to the static coefficient of friction times the normal force, we are able to plug that into the combined equation, and then plug in our knowns, and get 0.236. Sorry. What's going on here? Oh, I'm losing it. Okay, we're on 6. Sorry about that. I don't know what happened. Man, I'm just losing everything right now. What's going on? Okay, on 6. Okay, we're here. Six, the orbit of the planet Venus is nearly circular with the orbital velocity of 126.5 times 10 to the third kilometers per hour. And knowing that the mean distance from the center of the sun to the center of Venus is 108 times 10 to the 6 kilometers, we're supposed to determine the mass of the sun and the acceleration of gravity at the surface of the sun. So here are a couple force equations for planetary movements. F equals to G capital M little m over r squared. Force is equal to little m v squared over r. And we can combine those two equations to get G of m is equal to rv squared. And then we'll just change the radius from kilometers to meters, and the velocity from kilometers an hour to meters per second. Then we'll plug in those, and we'll get G of m is equal to 1.3335 times 10 to the 20th. And since big M is equal to gm over g, we can solve for m and get 1.998 times 10 to the 30th kilograms for the mass of the sun. And since force is equal to ma and force is equal to g big M little m over r squared, we can combine those two equations to solve for the acceleration at the surface of the sun. Plugging in our knowns, we get about 276 meters per second squared. All right. Number 7. We have a particle that's projected from a point with an initial velocity, and we're supposed to show that the force is inversely proportional to the square of the distance r from the particle to the center of the force O, using these given equations here. So if we plug in u is equal to 1 over r, we'll get this first equation. And if we simplify that down and we plug in for r, we will get this second equation. We take the second derivatives and we'll get this third equation. Simplifying it further, we'll get the fourth equation. And then solving for f, we see that f is proportional to f is inversely related to the square of r, since it's at the bottom there, in the denominator. Number 8. So there's a satellite in orbit 19,000 kilometers above the surface of the Earth. We're supposed to determine the speed required to achieve escape velocity and enter a parabolic orbit, and the decrease in speed required to obtain an elliptic orbit, and find the eccentricity as well. So first off, we want to find the velocity going around the Earth starting off just in a circle, which can be modeled by this first equation. Vc is equal to the square root of g r squared over r plus ho. We have all the knowns, so we can plug in and find what the velocity is around the Earth starting. And then we want to find the escape velocity, which is equal to the square root of 2gr squared over rho, over rho, sorry. And we also have all those knowns, so we can plug those in and get 5,500 89 meters per second. And since we're trying to find the increase in speed, we will subtract the elliptical orbit from the circular orbit to come up with 1,637 meters per second. That's how fast it would need to go. And since we know that the trajectory at any given point is 1 over r is equal to g of r squared over h squared plus c cosine theta, we can use that and solve for c. And knowing that the orbit has a close point and a far point, we can set the close point constant equal to the far point constant. And we come up with this equation. And since we know that theta when it's close and theta when it's far is 180 and 0, we can plug that all in and come up with h squared is equal to 2gr squared over 1 over RA plus 1 over RB. And since we know all those, we can go ahead and plug in the knowns. We'll come up with h is equal to 8.223 times 10 to the 10th meters squared per second. And we also know that R plus HO times VO is equal to H. So we can set those equal to each other, plug in our knowns, and get the initial velocity, which is 3,227.2 meters per second. Once again, subtracting that from the circular, we can get that we need to slow down 725.3 meters per second. And to find the eccentricity, we use this given equation here. 1 over r is equal to g of r squared over h squared times 1 plus eccentricity times cosine theta. We can plug in our knowns for r and all our other knowns and solve for the eccentricity, which should be about 0.33. Alright, so the last one, we need to show that 1 over rho is equal to 1/2 1 over RO plus 1 over R1. We need to show that the satellite's orbit can be expressed as that. So since we know that 1 over r is equal to g times m over h squared plus c times cosine theta, and we know that there is a close point and a far point, we can make those two equations, the close point and the far point, we can add them together. We can get this top equation here. And since we know that cosine of 0 is 1 and cosine of 180 is -1, they'll just cancel out, and we'll have 1 over RA plus 1 over RB is equal to 2gm over h squared. And since we know the acceleration is equal to v squared over rho is equal to h squared over r squared rho, and f is equal to g of m, big M times little m over r squared is equal to ma, we can combine those equations and find that 1 over rho is equal to g of m over h squared. And combining that with the equation at the top, we find that 1 over rho is equal to 1/2 times RA plus RB.